Okay, welcome back after this short break to the next talk by Jaz Myers from Johns Hopkins University. And David will talk about modal fracture of higher groups. Thank you, David.
Thank you very much, Benedict, and thank you for having me at this workshop. It's been really nice seeing the talks I was able to wake up for. So I'm going to talk to you today about the modal fracture of higher groups. So this is a internalization, or doing in HoTT sort of a result that I would cite to Schreiber. I'll tell you a bit of the history. And what it is it's taking a group-like object and it's splitting it up into its discrete and infinitesimal components. And that's the fracture part. So in fact, there are two sort of fracture squares, and you'll see one on the left here, one on the right over there. And they interlock and they form this hexagon. And, so if you get bored at any point during the talk, you can check out the paper on arXiv. It's listed there. And if you go to my website, which is davidjaz1z.com, you can find the slides. So let's start with a little bit of history. So back in 1973, Cheeger and Simons had just been working on some. Well, Cheeger and Simons introduced differential characters in order to set up some of the calculations that Simons had done with Chern with bundles and connections on bundles. And it turns out to be Deligne cohomology when interpreted in the differential geometric setting. So Deligne, around the same time, a little bit earlier, had introduced a cohomology in the complex analytic setting. And if you interpret it in the smooth category, you get the theory that Cheeger and Simons had called differential characters. And so in this guise, it becomes known as ordinary differential cohomology. Now, in 2008, Simons and Sullivan showed that the character diagram, which is drawn up here, this sort of hexagonal diagram relating the differential cohomology groups you find in the middle with the integral cohomology and the closed k+1 forms, the closed forms on a smooth manifold X, that this actually characterizes ordinary differential cohomology. It can be used to axiomatize it. And so there's a big gap, as you can see in this time frame, and in this time frame in between, there were a development of a lot of different differential cohomology theories, which is why we sort of separate out the ordinary differential cohomology equips ordinary cohomology, ordinary integral cohomology with differential form data. And so just a little bit more history, but now it's very recent history. Bunke, Nicolaus, and Volkel construct differential cohomology theories, and in general, so they give a general definition of differential cohomology, which includes other things than ordinary differential cohomology, like differential K theory, and they construct them as sheaves of spectra on smooth manifolds. And they show that in this setting, you can always make a hexagonal diagram like the character diagram, where everything is built out of the spectra in the center that represents your differential cohomology theory by applying certain functors that are defined on smooth manifolds. And around the same time, Schreiber showed that these hexagons, which are sort of seem to be characteristic of the differential aspect of differential cohomology, in fact arise from any adjoint modality comodality pair. And so this is the diagram written down there in terms of the spectrum alone. And so Schreiber shows that there's nothing actually fundamentally differential about differential cohomology. And indeed, in a NLab post called Differential Cohesion and Idyllic Structure, he emphasizes that they should be thought of as fracture squares, and that the traditional fracture squares even can be seen as instances of this general feature. So this is the kind of theorem that I'm going to put into homotopy type theory. So this is the main theorem we'll see today. So the modal fracture hexagon for higher groups. So this is an unstable version of a theorem of Schreiber, which does this for spectra. And it's also internal, so do it in homotopy type theory. So the theorem is that for any crisp higher group, we're going to construct this hexagon. The hexagon is called the modal fracture hexagon of the higher group. And it involves these two fundamental players. So down here, the shape G, that's the SG in the bottom corner here. I think if you can see my hand, that is the shape or homotopy type of G. And the fiber of the map which sends G to its homotopy type is the universal infinity cover of G. On the other hand, we have flat G, which is, we could think of as the underlying set of points of G, or the underlying space of points of G, discretely topologized. And this cofiber over here, well, it's not really a cofiber, but it would be if we were nice and stable, is called the infinitesimal remainder of G. And in a sense, it is G quotiented out by all its discrete points. So it's only what's infinitesimally left over. And these two things interlock in this hexagon. And what makes this hexagon special is that it's very tightly interlinked. So both squares are pullbacks, and the top and bottom sequences are fiber sequences. In addition to this, at the end, we can calculate that the shape of the infinitesimal remainder is a de-looping of the flat of the universal infinity cover. And so if you look on the left of the hexagon here, you see flat of the universal infinity cover, and here on the right, we have its de-looping. So if G can be further de-looped, not just once, but multiple times, and I'll do a refresher on what these terms mean in a second, then we can continue the hexagon and we get this sort of interlocking series of fiber sequences. Okay. So I'm going to begin with a quick refresher on cohesive homotopy type theory. So I'm going to be working in Mike Schulman's cohesive homotopy type theory. And what is special about cohesive homotopy type theory is that we remember that in constructive mathematics, in particular ordinary homotopy type theory, the proposition that every function from the reals to the reals is continuous is in fact undecided. There are models where in fact every function from the reals to the reals is continuous in the traditional sense. And since a function from a type to another type is defined by giving, assuming a free variable of the type, of the first type, and giving an element of the second type that depends on it in some way, we see that dependence on free variables encodes a liminal sort of continuity, the kind of liminal continuity that means that, well, there are models in which it would be actual continuity. So to make this actual continuity manifest, we can counterpose it with discontinuity. So another way to think about what we're doing here is we don't necessarily want all of our dependencies to be continuous. We want some of them to actually be discontinuous. So what Mike does is add these crisp variables, and these are free variables that express that the terms which depend on them will depend in a discontinuous manner. So to emphasize, we use a double colon to mean a crisp variable. And so a term, so this is adding another part to the context. And one thing I want to note is that this part comes to the left of the usual part. And what that means is that while continuous variables can have types that are crisp, crisp variables can only have types that are also crisp, that also only involve crisp variables. So a crisp term is a term which exists in a totally crisp context. And so then, now that we have these discontinuous variables, we can express this discontinuous dependence. We will internalize this by using a comodality flat. So flat A is going to be a type, and we can think of it as being inductively generated by the crisp elements of A. So I've written the rules up here just so that you know that I'm actually doing type theory, sort of. And so we can only form flat A when A is crisp. And if we have a crisp element of A, then we can flat it, upper flat it, to put it into flat A. And then the last thing here is an induction principle. It says that if we have a type C, which depends for its definition on a cohesive or regular variable of type flat A, and we have a term in flat A, and if we would have a term in the type C depending on a crisp variable of A, then we can sort of pattern match or inductively define a term in sitting over the actual term A of flat A. So the first thing we'll do with this is give ourselves a co-unit for this co-modality. So the co-unit is inductively defined by taking something crisp and sending it to itself. So I've written the pattern matching version, which is how this would work if you actually went and did this in Agda, since Agda supports the flat co-modality. And then below that, I've written what it looks like with the let notation. So are there any questions here? Maybe I shouldn't ask for questions. I don't know about how the Cloud Earth system works.
You can ask questions if they want in the chat or raising their hand. So it's perfectly fine to ask for questions.
Okay. So I'm asking for questions. Are there any questions here? And Benedict, you'll let me know. I can't look at the chat.
No questions so far.
Okay, great. Thank you. All right, so in addition to the flat co-modality, we have a modality called the shape. And the shape modality, we can think of it as a reflection into discrete types. So in differential geometry, the shape will be the localization at the real line. And this will take the homotopy type of a type because it takes a path, as in a map from the real line or the unit interval, but it's better to use open things in this setting. And it will collapse it into a point. So it sets points equal by it identifies points which have paths between them. And in fact, it identifies them by the paths between them. And I wanted to put another example here. This doesn't just work in differential geometry. It also works in other examples of cohesion. And in fact, we're only using the locally infinity connected portion of cohesion. We'll not use shape. We'll not use sharp in this talk. So another example is simplicial homotopy types, giving us simplicial cohesion. And here we could take shape to be the geometric realization, which is the localization at the one simplex. So just to make this more concrete, if we take the real n sphere, which is the type of points which are of unit distance from the origin, then the shape of the real n sphere is the higher inductive or homotopy n sphere. So this is a sense in which the shape takes the homotopy type of a space. So the real n sphere is a subset of the Euclidean space, and so it's a set, but its shape is a higher type. And so our axiom, which ties the shape to flat and to, therefore, our liminal discontinuity of the crisp type theory, is this one, which I call the unity of opposites axiom, channel Levier, that if we have a crisp type, and we need the type to be crisp, otherwise we can't form flat of it, which is co-modal for flat, the co-unit is an equivalence, then that happens if and only if it is modal for shape, the unit is an equivalence. And in either case, we say that X is discrete, or to emphasize, we might say that it is crisply discrete. And so Mike shows that this axiom implies that, or a related axiom, that for crisp X and Y, crisp types X and Y, we have an adjointness between shape and flat, at least when we take only the flatted mapping types. And the reason for that is if you look on the left here, shape X to Y, if Y had some kind of continuity, some kind of topology, then the mapping type would inherit that. Whereas here, there's a typo, that should not be an X, that should be a Y. Here, we flatted the codomain, so this would be a discrete type anyway, so we need to make sure at least this one is flatted here. And this is why that this adjointness is why Schaber has called flat, because if Y is a classifying type for something, then, so say it classifies some kind of principal bundles, then a map from X to Y is one of those things fibered over X. So it's say a principal bundle over X. And if that map factors through the shape of X, and let's say that the shape is the localization at R, this means that the thing classified is homotopy invariant. It depends only on the homotopy type of X. And in differential geometry, this is equivalent to equipping the thing with a flat connection. And so we see that flat of Y is the moduli type for things that Y classifies equipped with a flat connection. And that's why it's the symbol flat is used here. And we'll make that a little more concrete later in the talk. So now I need to tell you about the two main players in the modal fracture hexagon. So these are the universal infinity cover and the infinitesimal remainder of a higher group. So let me tell you what a higher group is. A higher group is a type, G, which is equipped with a pointed zero-connected type, BG, which we call the de-looping, and an identification of G with the loop type of BG. So the reason we think of this as a group is that the idea of what a group is a group is the symmetries of some object. So that object is the point of BG, and here we see that we're identifying G with the symmetries or self-identifications of that object with itself. Now the reason we want the BG to be zero connected is effectively that we don't want any other extraneous objects existing when we're studying this object that we're interested in the symmetries of. So we ask for BG to be narrowly defined. So if you have a symmetry of any object in any type, you can always restrict to all those things which are identifiable with it, and that will give you the de-looping of the symmetry higher group of that object. So that's the idea behind higher groups. So if we have a crisp higher group, and I'll just say a crisp higher group means everything involved is crisp. So in particular, it's a crisp type, which is crisply zero connected with a crisp point. So that's not I'll say that. Almost everything involved here will be crisp. That's how everything's going to work. So if we have a crisp higher group, we can define these two things. In fact, the universal infinity cover is definable for all types. But so if we have a crisp higher group G, then shape G is its homotopy type. And so the fiber of shape G is something like it's going to be contractible in the sense that shape of it will be the point. And that's because shape is a modality, and the fibers of modal units are always modally connected. And so this is a contractible type that sort of covers G, and it in fact has a very nice property, which is that it has a lifting property against shape equivalences or weak homotopy equivalences. And that is a work due to Felix Cherubini and Egbert Reike in modal descent. So they call these things modally atoll maps. And here, modally atoll map is going to be called, for shape, is going to be called an infinity cover. And this follows Felix's extended abstract cohesive covering theory. So the universal infinity cover is the contractible infinity cover. And it works a lot like a regular universal cover, except that it has a lot of higher structure, even if G was a set. On the other hand, we have the infinitesimal remainder, and we can think of this as the quotient of G by its underlying type of points, flat G. So the way we define it is by the fiber of the flat inclusion of flat BG into BG. And by continuing that fiber sequence, we can see that it's therefore the homotopy quotient of G mod flat G. And so the reason I've written it with this little lowercase math baby G is because in many respects it behaves like the Lie algebra of a Lie group. In fact, in differential geometry, it is the closed one-form classifier for one forms valued in the Lie algebra of the Lie group. And this theta behaves like the Maurer-Cartan form. So this way of thinking is by way of Schreiber. But it completely abstractly, with no relation to differential geometry, we can prove a bunch of lemmas that make it feel like the Lie algebra of a Lie group. So in particular, the infinitesimal remainder of a higher group and of its universal infinity cover are equivalent, just like the Lie algebra of a Lie group and its universal cover are equivalent. So now we can come to proving these sort of fracture square results. Here are two pullback squares that we're going to prove. So for a crisp higher group, so these relate the two aspects. They relate the universal infinity cover, which was defined by Shape, to the flat modality, and it relates the infinitesimal remainder, which was defined by flat, to the Shape modality. And the proof that both of these squares are pullbacks effectively comes down to just showing that the fibers are merely crisply discrete. So they are merely discrete. And so in the first one, we can show that by continuing the fiber sequence from defining the universal infinity cover, that the fibers of pi are identifiable with the what you could call the fundamental infinity group of G, the loops of the shape. And that's crisply discrete. And then you prove a lemma showing that a map with crisply discrete fibers has a pullback of this sort. And on the other hand, we can show that the infinitesimal remainder is itself an infinity cover, which means that this naturality square here is a pullback. And we can do that again by showing that its fibers are merely crisply discrete. So the fibers in this case are all identifiable with flat G. This is effectively a transitivity. The action is transitive, so we can identify them all with flat G. So therefore they're all crisply discrete. And by the good vibrations trick, which is what I like to call the main theorem of another paper, good vibrations through the modal prism, this implies that theta here, the quotient map, is a infinity cover, and therefore that this square is a pullback. So this is the idea of those proofs. So now we can put the two together to get the modal fracture hexagon. So the modal fracture hexagon is up top, and we've shown that the two squares are pullbacks, so it just remains to show that diagonal sequences are by definition fiber sequences. So it just remains to show that the top and bottom sequences are fiber sequences. So the top sequence is a fiber sequence by the lemma that the infinitesimal remainder of a higher group and of its universal infinity cover are the same. So that's actually just the fiber sequence defining the infinitesimal remainder of the universal infinity cover. And the bottom one we get by applying the respective modalities and comodalities to the two defining sequences. So if on the left we have the defining sequence of the universal infinity cover, and on the right we have the defining sequence of the infinitesimal remainder. And on the left, if we apply flat, we get a sequence written below in orange. And on the right, if we apply shape, we'll get a sequence written below in orange. And I should say that to apply shape so flat is left exact. This is a theorem of Mike's in the cohesion paper. But shape is not left exact for good reason. But there are certain maps on which it does preserve fiber sequences, and they're called the shape vibration. So using a little bit of the shape vibration tricks, we can show that in fact it does preserve this fiber sequence. And so what we end up with, if you squint, is that we have the same sequence, but it's shifted over. And in one side we have flat BG infinity, on the other side we have shape little g. So in particular in here, we've shown that the shape of the infinitesimal remainder is a delooping of the flat of the universal infinity cover. And this completes the main theorem. So I want to show how we can use this to do some more classical things. So I want to show how we can actually go back to ordinary differential cohomology in this setting. And it turns out that, well, nothing about the modal fracture hexagon had anything to do with differential structure. It's all about these adjoint modalities and comodalities. So to go to ordinary differential cohomology, we have to add some differential aspects to our theory, and we'll do that in the form of this assumption here. It turns out that this is also quite abstract, so I'm going to present it in the abstract way. But we're going to assume that we have form classifiers, and externally these would be the sheaves that sends a smooth manifold to its set of K-forms. And so we're going to assume that they're abelian groups, they're crisp assumptions, I should say, and that we have crisply an exact sequence like so. So this is the exact sequence that the exactness of this sequence sort of externally corresponds to de Rhams' theorem for at least Euclidean spaces. And we'll ask also that the form classifiers are contractible. So if we define the closed form classifiers to be the kernel of these differentials, we'll also want to assume that these are infinitesimal. Now, in fact, the form classifiers themselves are infinitesimal, but you can get away with a little less, so we'll just assume this one. So there's nothing in this assumption that actually means these are form classifiers. In the abstract, I would call this a contractible and infinitesimal resolution of an abelian group, the abelian group here being R. But I'm going to talk about it this way because it's a little more concrete. So one theorem you can prove from these assumptions straight away is that the shape of the closed form classifier is flat BKR. And so the shape unit goes from the K-form, the closed K-form classifier to flat BKR, which represents discrete real valued cohomology. And so this is the de Rhams class. And what this theorem says is that the de Rhams class is the universal discrete invariant of closed K-forms. And so now we can define the classifiers for circle K-gerbs with connection. So we're going to define it by this pullback. We're going to equip integral cohomology data with differential form data. And so we make this defining pullback, and I've colored it according to how these things will appear in the modal fracture hexagon. And once we've done this, we can do a bunch of work, like show that actually there is an underlying circle K-gerb from this, and that the top map, which goes from BKU1 to the K+1 closed form classifier, that the fiber of that is in fact flat BKU1, and therefore that map as an abstraction to flatness is the curvature. We can also show that the green map listed there is the shape of the classifier with connections. And we just go all the way through. And by the end, what we end up with is this theorem, which is that we calculate the modal fracture hexagon of the classifier for circle K-gerbs with connection to be this diagram. So we have the map that takes the curvature, we have the underlying topological class of our differential cohomology class, and these are made by a pullback over the de Rhams class, or the inclusion into the real numbers, or really the tensoring up into the real numbers. That's on one side, and on the other side we have a relationship between the flat connections. So this other thing on the top left corner over here is maybe a little unfamiliar. This is my notation for it. This is what I call pure differential cohomology. And you can see that the pure differential cohomology is sort of one way to define it is it's the fiber of the de Rhams class. And it's also the fiber of the topological class and differential cohomology. So it is pure differential cohomology is what's left of differential cohomology when you have a vanishing topological class, when you vanish in integral cohomology. And from here, we can pass to ordinary differential cohomology by taking truncations in the normal way, but there's a slight little itch that stops us from getting to the very traditional square, and it has to do with de Rhams' theorem in modal homotopy type theory. So if you're interested in that, I can talk about it, but I think that this will end my talk. Thank you very much.
Thank you very much, David. Let's give a round of applause. We have time for one question before we will be automatically boosted to the next room. Anybody wants to ask a question? Okay. Well, if you want, you can of course discuss in the discussion room that Malena posted a link to, or you can discuss after the next talk, which will also be the last talk. See you there.
Live, but